The video you're about to watch will be detailing the experiment on how to use a plane mirror and an object to create an image and compute the angle of incidence, the angle of reflection, and also project the image. This falls under the lab entitled Reflection, Refraction, and Lenses. So basically, for this lab session, or this particular experiment, should I say, we'll be using a couple of tools. We will have pins here to help us locate the position of the object, the position of the image. We will also have a plane mirror right here. Now, because everything will be happening from quite a different angles, at some point in time we will need a block to provide some sort of support to the mirror. We will also need a ruler to draw some lines, and we will need a protractor, which I will make you see right here. And those are the tools for the part that consists of reflection. So how will that work? As you can see, if I take the box, the mirror, and my pins off from the workstation here, I have an empty box which I've flipped over, right? And on that box, I will lay an A4 format plain sheet of paper, okay? And then next thing I will do is I will place a block on one of the length side of the paper. Now the purpose of this block is to help support the mirror as I conduct the experiment. So the mirror can sit there with no problem. Now what we know about plane mirrors, as you would have seen in the previous video, is that they are smooth and they reflect light coherently. That is, the angle of incidence and the angle of reflection are the same because of the smooth nature of the mirror. And that is what we're going to try to experiment. So how are we going to do this? We're going to do it a couple of ways. So after we put a mirror here, we're going to pick two pins, which are going to be our object pins, which I will in this case call pin 1 and pin 2, right? I particularly chose the ones that have the little white beads at the end so that you can distinguish them on the video. And then we will have two other pins, which will be pin 3 and pin 4, which in this case I chose to take the pins that have no beads at the end. So the way that works is I will map out my box. Let me get a pencil. I have to map out the position of the mirror such that even if something happens, in the event something happens, I am able to put back my tools in place. So bear with me. Let me map out the block supporting the plane mirror. That will be our surface of reflection. All right. So here we go. I take my block off, right? I take the mirror off. I put my block on the paper, and let me put it here. Map out the position of my block right there. Now, what this helps, how does this help? In case for some reason my things fall apart, I'm always able to locate the position of whatever I was doing. And now I can put my mirror right there, and the mirror is supported. Now, one of the approximation that we'll make is, even though the mirror has a certain thickness, we're going to behave as though the mirror lines up, as though it has no thickness, as though this line is a reflective surface, okay? I'm actually considering maybe moving things around, but we'll see. Now, the next thing I'm going to do, I'm going to put pin 1, all right? So I hope you guys can still see. I'm going to move things down later on, but I want you guys to have this top view because a lot of things will be happening. So I'm going to go away from my mirror to the very edge of my paper here, and I'm going to put my object, all right? I'm going to put my object right here. So this is pin 1. And the way I'm going to put pin 2 is I'm going to match my line of sight, right? That is the way I look at an object, the way I place my head when looking at an object. I'm going to, first of all, I'm going to close one eye, which in this case will be my left eye, and I'm going to focus on pin 1. And subsequently, I'm going to go towards the mirror and try to match the object pin 1 with pin 2. That is, I want to overlap pin 2 and pin 1 in my line of sight. So I want it to be possible that when I look at pin 1, I do not see pin 2 because pin 2 is aligned with pin 1, and then I will put my pin 2 into my cardboard box. So there you go. I have my pin 2 in place in a straight line with pin 1. All the two of them are lined up to my line of sight. What do I do next? The next thing is I will take pin 3 and I'll move to the other side of my experiment. So initially I was looking at things from this side, from this perspective. I placed my head somewhere in this direction, in this position, looking through the line of sight of pin 1 and making sure it matched with pin 2. Now I'm going to place my head in this direction, and the goal will be to make sure that I see things now from another perspective, from the perspective of the reflected image. So pin 3, again, I'm going to shut my left eye and I will look at everything with one eye. Now, the reason why we shut off one eye and keep the other open is just because we want to be able to focus on just one, what is the word here? One perspective of the whole setup. You know, when you look at objects with your two eyes, what it actually does, it wants to give you a broader and more 3D view of the object, which is not really what we want here. What we want is to be able to see things from a very unique perspective, such that it's just a single ray, it's not two rays. Two eyes entails you dealing with two beams of light, right? We want to use just one beam of light, which in this case we'll consider to be like one ray. So with my left eye shut, when I did this first part of the experiment, what actually happened was my eye played the role of a ray, and the ray went from pin 1 to pin 2. That is why my goal was to make sure that pin 2 was concealed. When looking at pin 1, I couldn't see pin 2 because pin 2 was hidden behind pin 1, and all of the two were in my line of sight. So now what I have to do is move my head to this other side of the experiment setup, and I will put pin 3 in such a way. Now again, my left eye is shut. I will put pin 3 in such a way that pin 3 will cover up the image of pin 2. So I have my eye shut, and I can see an image of pin 2 on the mirror, and I will put my pin right here. I'll put my pin 3 such that it covers the image of pin 2. Not pin 2 though, it's going to cover the image of pin 2 on my mirror. All right, so this is me covering up the image of pin 2. And still in the same position, I am going to put pin 4. Now pin 4 is going to be farther away in the same line of sight, and the condition for pin 4 will be pin 4 has to overlap pin 3, overlap the object pin 3, just like we did with pin 2 concealed by pin 1. Here pin 3 will have to be covered by pin 4. So I'm putting pin 3 here such a way that when I look at pin 3, when I look at pin 4, I cannot see pin 3. So again, I put everything in my line of sight. Remember, one of my eyes is closed. So here's me putting down pin 4. All right. Okay. So when I look at this, I cannot see pin 3 because pin 3 is hidden behind pin 4. Same thing happened previously where I couldn't see pin 2 because it was hidden behind pin 1. Now, with this done, this is the complete setup for the experiment of reflection. Now, that was just the setup, right? Now we need to collect the data and compute the results. How do we do that? Now we can take off everything because the pins allow us to see the position where the objects were. The way we mapped out the block allow us, right, to see where the mirror was, okay, I can do an extra line on the position of my mirror just to make sure I know where the mirror was. So now I'll take my plane mirror off, I'll take my block away, and I can pull out the pins because the pins have created holes on the paper that I can trace easily. So I know you guys can see this clearly. Let me see if I can zoom. Unfortunately, no. Let me see if I can take this down a little bit. And all right. I'm trying to give you a broader view of what was happening here. All right. It's my way of zooming by bringing the camera closer. All right. I'm going to add one more thing to this, so bear with me. Let me see if we need a source of light maybe to improve the video. Hold on. Next thing now is I am going to connect the hole made by pin 1 to the hole made by pin 2. That symbolizes what we call the incident ray, which is the incoming ray. So my pin 1 was here, my pin 2 was there. So I'm going to connect the two holes bored by those pins. And I'm going to extend that line past the position of my plane mirror. All right. Likewise, I'm going to connect the hole made by pin 3 and pin 4 with a ruler. All right. All right. And again, I extend that line past the line created by the plane mirror. The line created by the plane mirror is a surface, okay? And the point of incident is where the incident ray hit that surface. So we're going to go to where the incident and the reflected ray intersect, and we're going to draw the normal. The normal is a line that goes off the point of incidence. That is the point where you have the incident and the reflective ray, the kind of intersect at a given point on the surface. And the normal ray is a ray perpendicular to that point on that surface. So if this is the surface, a line that is perpendicular or right angle to that surface and that contains my incident and reflected ray is this line. All right? So I'll call this my normal. I call this my incident, and I call this my reflected. It's kind of hard to go around these things. Excuse me. All right. So the next thing you want to do is collect the data. Well, the data here are the angle of incidence and the angle of reflection. So those angles are obtained by placing a protractor on the surface and measuring the angle between the normal and the incident, which we will call the angle of incidence, and then the angle between the reflected ray and the normal, which will be the angle of reflection. So here we go. From my reading here, the angle between the normal and the incident is the space between the angle 90 degree and the angle 67. So between 67 and 90, that means I have about 23 degrees. So my angle of incident here is 23 degrees. All right. My angle of reflection is sustained by an angular distance going from 90 degrees to 110 degrees. All right, and that is worth approximately 20 degrees. In an ideal world, right, the angle of incidence and the angle of reflection will be the same. But this is not an ideal world, right? This human error. So these numbers 20 and 23 are pretty close, right? So this concludes the practical part of the reflection experiment. We will collect this data, and on the other video we're going to process it to do some computation